Okay, so sorry about that. I had to change rooms. So let me redo that example. So here's the example with the cell phone users. Okay, so let me just redo this. Okay, I'm not going to redo the whole thing, but you're doing a 95% confidence interval for P1 minus P2, where we said that P1 is going to be the proportion of whites that are cell phone users, and P2 is going to be the proportion of blacks who are cell phone users. And we want a 95% confidence for the difference between those two populations, okay, those two proportions. And so what we did was we have whites here and blacks here, and so what I did was I wrote down the information. So P hat here, so P1 hat from the problem is 10% or 0.10. P hat 2 from the problem is 5%, which is 0.05. And then they gave us N1 for the white sample. That was 1,343. And N2 was 232. So now here's the formula again. It's going to be P1 hat minus P2 hat plus or minus Z alpha divided by 2 times the square root of P1 hat Q1 hat divided by N1 plus P2 hat times Q2 hat divided by N2. And so if we just take this information that they give us in the problem and plug and chug, we'll be able to get it. And we should know, remember, that a 95% confidence level, if we use the table for our normal distribution, or we use inverse norm, we'll get a z-score that's equal to 1.96. Okay, so if we plug in here, we get 0.10 minus 0.05 plus or minus 1.96 times, what do we get here? Well, we get 0.10 times 0.9 divided by N1, which is 1343, plus 0.05 times 0.95 divided by 232. Okay? And so if we write this down, let me make sure there's no glare. Can you see that? Let me get the glare. So if you write that down, then and just plug it into your calculator and just plug chug, you have the answer. Okay, so now all I'm going to do is take my calculator and calculate the margin of error. And so what do we get? We get 1.96 times the square root of 0.1 times 0.9 divided by 1343 plus 0.05 times 0.95 divided by 232, and we get 0.032 as the margin of error. 0.032. And this is just going to be 0.05. So our confidence interval turns out to be what? Well, 0.018 to 0.082. Now, the thing is with proportions, you want to write them as a percentage. So the way I would write this is 1.8%, comma 8.2%. Now, again, the way we subtracted these, right, means that, hey, it's positive, right? We have positive percentages, which means this proportion tends to be smaller than this proportion. So it's in favor of whites. So it seems like that the proportion of whites that are iPhone users is anywhere from 1.8% to 8.2% higher than the proportion of black iPhone users. That's the interpretation. And we can be 95% confident that the true difference between the two population proportions is somewhere between these two numbers. Okay? And again, so that wraps up chapter 10. Okay, next time is chapter 11, and which we're going to get into variances and hypothesis testing, and we're going to deal with a new distribution called the chi-square distribution. So apologize for the interruption. There was a class that came in, so I had to quickly change rooms. So that's it. Talk to you later. Okay, welcome back. And today we're going to talk about a new distribution called the chi-square distribution. And this is going to start chapter 11. And so in chapter 11, we're going to now talk about other hypothesis tests that we can do, tests that are going to tell us something about the variance of the population, tests that will compare two population variances, confidence intervals involving one sample, okay? And so in chapter 11, we're going to deal with one sample hypothesis testing for either standard deviation or for variance. And then we're going to talk about confidence intervals. And then we're going to talk about three specific tests that are used with this new distribution that we can test specific things. Okay, so where this comes from is the idea that certain things that we would like to know, questions that we would like to answer, and so this chapter is about answering those types of questions, and they involve the variance of a population or the standard deviation of a population. And so the way we're going to start is asking a couple questions. So here are the questions. So have you ever wondered if lottery numbers were evenly distributed or if some numbers occurred with greater frequency? How about if the types of movies people preferred were different across different age groups? What about if a coffee machine was dispensing approximately the same amount of coffee each time? So you could conduct a hypothesis test to answer those questions. And the hypothesis testing that we're going to talk about in this chapter will do just that. Okay? And so we're going to define a new statistic. And so what we're going to do is look at different samples. So again, just like the little experiment that we did in chapter 7 about sampling distributions, now we're going to talk about sampling distributions that involve standard deviation or variance. So we're talking about S and S squared. So now, if we took a sample of size n from a population where we know the standard deviation, and we calculated the sample standard deviation, and we did this over and over and over again, we could figure out, and we'll find out that we could create this statistic that will have a special distribution. And the distribution that we're going to talk about is called the chi-squared distribution. So the chi-squared distribution is a distribution based on this calculated value. And this is the formula for that value. And this is called the chi-squared random variable. And this is the Greek letter chi. Of course, we're squaring it, so that's where the term chi-squared comes in. And I'm not going to get into the derivation of this or where this comes from. But suffice it to say that this is going to have a distribution that compares the sample variance to the population variance. And n-1 is the degrees of freedom that we've talked about before. And it's based on the calculation for the sample standard deviation. So now, what does this look like? Well, it depends on the sample size, but it typically will look something like this. So it starts at 0 and goes off to positive infinity. So it's the values of the chi-squared random variable is always greater than or equal to 0. Okay, and so it could have something like this. Now, here are some examples in the textbook, and I'm just going to hold them up to the camera here. So notice that for the top one, it almost looks like an exponential curve where the degrees of freedom is 2. And it's, I don't know if you can see it, but it's slightly, and then below that has a degrees of 6. And so if you notice the lighter one goes straight up, sort of like the one that I have on the board. And notice that when the degrees of freedom is 12, it's a little bit more like a normal curve, but it's still very skewed, but you've got that unimodal distribution. And of course, as you could tell, as the sample size gets larger and larger, this will become more normal. But even for really large sample size, the chi-squared distribution tends to still be slightly skewed. Okay, so keep that in mind. So the main characteristics that you want to keep in mind is that all chi-squared values are greater than or equal to 0. That should make sense because variances, sample variances, or population variances are always positive, and n is always positive. So you're never going to have something that's negative. Okay? There's a different chi-squared curve for each degree of freedom. So this represents a family of distributions, just like the t distribution is a family of distributions. It depends on the degrees of freedom. So as the degrees of freedom increase, the shape of the distribution for the chi-squared distribution changes, as you saw in the picture. The curve is non-symmetrical and skewed to the right. That's obvious. The total area under the curve is 1, or 100%. Okay, so that's important to know. The notation for a random variable. So if we have a random variable x, we would say that the random variable x follows a chi-squared distribution with degrees of freedom as a subscript. So if the degrees of freedom is 11, then we would write it as chi-squared with a subscript 11. Okay, so that's the notation that we use for chi-squared. Very much like the same way we denote a t distribution. So if we say x has a t distribution, we would use lowercase t with a subscript of degrees of freedom. Okay, so now, a couple of things to note. let's see here. I don't want to do that. Let's see, what do I want to say about this? Yeah, let's just talk about critical values. So one of the things you're going to need to know how to do for a chi-squared distribution is find the critical value. So when you talk about doing hypothesis testing, or when we talk about doing a confidence interval, we need to know what the critical values are. Just like when we dealt with the t distribution and the z distribution, we had to figure out what the critical values are. Well, the one little catch here that we have to keep in mind is that the chi-squared distribution is not symmetric, okay? So we have to calculate both critical values separately, okay? So in other words, typically when we do chi-squared, the chi-squared value here, for example, we would notate as chi-squared alpha, where alpha is the area to the right, okay? Now, if we had a chi-squared value over here, then again, we could call this chi-squared alpha, but alpha again is the area to the right. Typically, we would say this left chi-squared value would be 1 minus alpha, okay? If it was a one-tailed test or you just wanted the area in the left, think about hypothesis testing. So the area to the left would be 1 minus alpha here. If we were doing a right-tailed test, it'd be alpha, where alpha is, again, the area to the right. It's one of the rare things where it's always area to the right. With the chi-squared distribution, we're always concerned with area to the right. Alpha is always area to the right, okay? But what we typically say, and the textbook does this, instead of using alpha and 1 minus alpha and alpha divided by 2 and this and that, what we could do is we could use chi-squared r for the right critical value and chi-squared L for the left, okay? And then you just have to make sure that what alpha level you're looking at. Are you looking at alpha divided by 2 or alpha, okay? But that's going to just come from practice and knowing what you're looking for. Okay, so now, let's think about critical values. So now let's give a couple of examples. So let's say we have a critical level, or a confidence level. So let's say we have a confidence level equal to 0.9. And therefore, alpha, which is equal to 1 minus the confidence level, is 0.10. Okay? And let's say we wanted to find the right and left critical values for a confidence interval, let's say. Well, just the process is exactly the same as we did before with the other confidence levels. The confidence level is the middle area. So we know that the middle here is 0.9. And so between these two chi-squared values is 0.90. And then of course alpha is the area in the tails. So what do? We take half of alpha, and so that means 0.05 is here. And we take half of alpha here, and that's going to be 0.05. And so now we have what we need to find the critical value. The only problem is we have no function on your calculator to find it. You have to use the table. Okay? So I'm going to show you the table, and what we're going to need to know are two things. We need to know alpha. Okay, so we need to know alpha, and we need to know the degrees of freedom. Okay, so now let me do an example. Let's say n is 15. So in this case here, the degrees of freedom would be 14, right? And so now this is the other piece that we need, is the degrees of freedom to use the chi-squared table. So what we're going to do is we're going to use that information and we're going to look up those two things on the table. Okay? So now let's do that. So alpha is 0.01 or 0.1 and degrees of freedom is 14. So notice on the chi-squared table here, I'm going to hold it up. So notice at the top, it's area to the right. Alpha is always area to the right. So notice something, that if you look, you've got your alpha level and that big bold line in the middle separates the right side of the graph from the left side of the graph. So all the numbers on the right side are the right critical values, and everything on the left side is the left critical values. And so what you need to do is you need to find, and look at the picture. The picture always gives you area to the right. Okay? So now what you need to do is look for your alpha level. Okay, that's one thing. And then once you find your alpha level, then you go down that column and across the row. Now where's the row? Well, the row is the degrees of freedom. So here you look for your degrees of freedom down here. And then notice the subscript here is alpha. Okay? That's area to the right though, right? So if you look over here, it's 0.005, 0.01, 0.025, 0.05, 0.1. And so these are all alpha, right? So the subscript is telling you your alpha, okay? Here on this side is the left-hand side, but notice how the subscripts are all larger, right? So what you have to do is, it's 1 minus this is your alpha, okay? So again, I would write at the top of these what the alpha is. In fact, let me do that. I'm going to do that right now so you guys see. And so hold on one second. Okay, so now notice here on the table now. So at the top I wrote all the alpha values, right? So now here are the alpha values that correspond. So now notice that it goes from 0.1, so it's symmetric on both sides. So if you do this side, all you have to do is look at the subscript, and that's your alpha level, okay? So just look for your alpha level. On this side, just look at the top here, and this is your alpha level, okay? And then what you do is you look for your degrees of freedom. So in this case, you go down to 14, okay? And so if you look at 14 and you go across the 14, so again, you're going down 0.05, right? That's your alpha divided by 2, right? Because it was 0.1, so we cut it in half. So alpha divided by 2, so you look for that alpha level, and there's your first critical value. And then if you go to the other side and you look for your alpha level, 0.05, and you go down that row, and there's your other critical value. So that's how you use the table, okay? So now, based on that, we know when you look at the table, chi-squared L is going to 6.571, and chi-squared R is going to equal 23.865. Okay? So again, practice looking up the chi-squared values using the table. Okay, because I'll supply a table, usually you'll have a table supplied to you because there's no function on your calculator that will give you the critical values. Okay, so you have to use the table, there's no way around it. Okay, so now, let's see. Let's see here, how do we want... Okay, so we did that. Now, let's do another one, just to hit the point home. So let's say you have you want to find the left and right critical values for a chi-square distribution where the confidence level is 0.98. And the degrees of freedom is 6. Well, again, that means the middle area here is 0.98. And if we take half of alpha, then we know that this area has to be 0.01. And this area also has to be 0.01. And so now when we go to the table, we're going to look up degrees of freedom, and alpha is 0.02. So we're going to look up 0.01 on either side, right? Because we're dividing by 2. Okay? So on the right side, I'm going to look up 0.01. And I'm going to go down to the degrees of freedom is 6, and it's 16.812. And if I look up the other side, 0.01, and I go down to 6 degrees of freedom, it's going to be 0.872. So pretty small. Okay. And that's it. So practice using the table. So now let's talk about confidence intervals. So now that you know the formula for the chi-squared statistic, and you know how to find a critical value, let's talk about confidence intervals for either the variance or standard deviation. So the confidence level, or confidence interval, for the variance or standard deviation are based on this idea of how do we calculate the chi-squared statistic. So we start with this here, and we know that this is equal to what? N minus 1 times S squared divided by sigma squared. And this is under the assumption that we know what the population standard deviation is. But what if we don't know what the population standard deviation is, and we want to find a confidence interval? Well, let's solve this for the variance. So we can do that, and what we will get is we get sigma squared is equal to n minus 1 times s squared over chi squared. And now what we want to do is we want to, again, capture, let's say 95%, right? So we want to capture 95% of all the possible chi squared values that we can get. Or in other words, 95% of all of the possible sample variances, okay? And it amounts to the same thing. So what we want to do is we want to find the two chi-squared values where we can capture 95% of all of the chi-squared values in between, right? So the middle 95%, just like we did before, okay? So how are we going to do that? Well, it's going to be two values for sigma that are related to this formula. So why don't we do this? Well, we're going to want to be in between. We want sigma to be between two values, right? And this is going to be the same. That's not going to change. This isn't going to change, right, on a specific sample. Well, actually, hold on. This is going to change, right, because it's the sampling distribution. This isn't going to change because we're going to stick to one fixed sample size. And based on that sample size and the confidence level, we're going to get a specific chi-squared value, right? So, in fact, we're going to get 2, right? Because we want the middle to be 95%. So we need to capture 95% of the middle, okay? So now, how are we going to do that? Well, what we're going to do is we need sigma to be in between two values. And we're going to compute those values using these formulas. And so, how do we determine where the values are? Well, this and this are going to be the same. The only thing that's going to change is this. And it's going to be based on exactly what we've been doing. The critical values. So we need to find the left and the right critical value, and then we're going to put the right critical value on the left, and we're going to put the left critical value on the right. And the reason why is because the right critical value is larger, right? That's the larger one, and we want it over here because this is going to be the smaller endpoint, right? So the greater than or equal to. And then the smaller one goes here, and so that's why we do it that way, okay? So now, and remember the degrees of freedom is n minus 1. And the point estimate that we're using is the sample variance, okay? So we're using the sample variance to calculate the confidence interval, okay? Let me see if there's anything else. So now this is the confidence interval for the variance. Well, what if I wanted the confidence interval for the standard deviation? Well, all I'm going to do is square root all three pieces. So it'll just become n1 times s squared divided by chi-squared r is less than or equal to sigma, which is less than or equal to the square root of n minus 1 times s squared over chi-squared l. So that's the only difference, okay? So based on whatever the confidence level is, right? So the confidence level will tell you your alpha, right? Because alpha is 1 minus the confidence level. And then you're going to take alpha divided by 2, and that's going to help you get your chi-squared r and your chi-squared l. And you have to use the chi-squared table to do it, okay? I hope that makes sense, because that's really all there is to it for the confidence intervals for sigma. So let's use an example. So it says in weights, the weights in pounds of 15 dogs selected randomly from those adopted out by an animal shelter last week are shown in the list below. Construct a 98% confidence interval for the population variance. Okay, so we want a 98% confidence interval for the variance. What is the variance? It's the variance in the weight of dogs. Dogs from this particular animal shelter. And so here's the data. I'm going to make sure I don't want to... Okay, so here's the data I'm going to write out. So these are all the weights in pounds. 25, 34, 27, 27, 31, 28, 33, 31, 28, 29, 32, 29, and the last one is 29. Okay, I just want to make sure I get all those on there. Okay, I did. So now, those are the 15 weights of the randomly selected dogs. So now, based on this, I want to construct a confidence interval. Well, the first thing I'm going to do is put this in L1, in my calculator. So I'm going to put this list into L1. Okay, so while you guys are doing that, I'm going to do that. If you'd like to pause, you can, but I'm going to take time to put it in here. Okay, so I'm just going to double check I have everything in here right. So 25, 34, 27, 27, 31, 28, 31, 28, 27, 28, 33, 31, 28, 29, 32, 29, 29. Okay, so now I've got my data in the calculator. So now, what's the formula for the confidence interval? Well, the formula is, what is it? It's going to be n minus 1 times s squared over chi squared r, which is less than or equal to sigma squared, which is less than or equal to the same thing, n minus 1 over s squared over chi squared r now, or excuse me, L. And so I know the degrees of freedom, that's going to be 15 minus 1, so it's going to be 14. Now I don't know s squared, but I'm going to get that from the calculator. So I'm going to go to second calc, or I'm going to go to stat calc, 1 var stats, and I'm going to go to my list. I'm going to enter my list. And now my standard deviation is 2.5128. So I'm going to square that, or 2.513, 2.513, and I'm going to square that. Now I know it's going to be the same on both sides, right? So I'm going to just go ahead and put that in there. So this is going to be 14 times 2.513 squared. Now, I just have to look up the critical values. Well, that's what I'm going to do right now. So, for 14, and a confidence level of 98, so that means what? Alpha is equal to 0.02. Half of alpha is equal to 0.01. So I'm going to look up 0.01 and the degrees of freedom 14. So if I look up 14.01, my critical value, my left critical value is 4.660. My right critical value is 29.141. And so now all I have to do is plug and chug into my calculator and write down the answer. So 14 times 2.513 squared divided by 29.141. And I get 3.03. So 3.03 is less than or equal to sigma, which is less than or equal to 18.97. So now my confidence interval is 3.03, comma, 18.97 pounds, or well, pounds squared, okay? So what can I say? I'm 98% confident that the true variance for the weights of dogs, dogs at this shelter range from 3.03 pounds squared to 18.97 square pounds, okay? And of course, if you wanted the standard deviation, you would just square root of everything. And that would give you the standard deviation, the confidence interval for standard deviation. Let's see here. Now, let's see what else we got. Let's do another one. So here, it says a random sample of 18 men have a mean height of 67.5 inches and a standard deviation of 1.5 inches, constructing 99% confidence interval for the population standard deviation. So now, what do they give us? Well, we know n is 18. The mean height, x bar, is 67.5 s, so because it says the standard deviation for the 18 men, so s is 1.5, and they want to construct a 99% confidence interval for sigma, the standard deviation of heights for all men in this region, in this population. So now, we're going to use the same formula. So all we're going to do is we're going to use sigma is less than or equal to, or greater than or equal to, the square root of n minus 1 times s squared over chi squared L. And again, we'll have the same thing over here. So it'll be square root of n minus 1 times s squared over chi squared R. And so now we have everything except the critical values. So again, the confidence level tells us what alpha is. So alpha is equal to 1 minus the confidence level, right? Which is going to be equal to 1 minus 0.01, or 0.99 rather, sorry. And so that's going to be equal to 0.01. And of course, alpha divided by 2 then is 0.005. And this is what we're going to use for our alpha because it's a two-tailed test. And our degrees of freedom, right? Our degrees of freedom is 17. So now, what am I going to do? I'm going to look up the critical values. Let me look up the critical values. So I'm going to use the table, and so I'm going to look for 0.005 on both sides. and I'm going to go down to the 17 degrees of freedom. So 0.005 gives me a critical value of 5.697. 5.697. And on the other side, the right, or the left, hold on a second, wrong one, this was left. Left is 5.697. And then the right side is going to be 35,718. And now I'm just going to plug and chug the rest of it. So this is going to equal the square root of 17 times, it's going to be, S is 1.5, so that's going to be 2.25 squared. So it's going to be 1.5 squared over 35.718, less than or equal to sigma, less than or equal to the square root of 17 times 1.5 squared over 5.697. So now again, I'm going to calculate. So 17 times 2.25 divided by 35.718. So we get 1.07 on this side. So 1.07. And on the right side, we get oops, hold on a second, I forgot something. Hold on. Forgot the square root. My answer. Okay, so this side will be 2.59. And this will be 1.03. And so that's my confidence interval. So my confidence interval is going to be 1.03, comma, 2.59. So I know that the true standard deviation of the population, which is the heights of men in this particular population, so the standard deviation of heights of all men in this population will be somewhere between 1.03 inches and 2.59 inches. And that's it. And I can be confident that it's 99% confident. So I'm 99% confident that the true standard deviation for the heights of all men in this population is somewhere between these two numbers, these 2 inches. Okay? Okay, that's it. So now, let's see here. Okay, so what we're going to do is, so that's with confidence intervals, introduction to chi-squared and how we would use it for confidence intervals. Next time we're going to talk about how do we do hypothesis testing involving one sample for either standard deviation or for variance. So this is going to be for a single variance or a single standard deviation. But again, it's going to be the same test as you'll see. So until then, I'll talk to you then.